neurotransmitters in mental disorders. What if the difference between happiness and depression, clarity and confusion, or even sanity and madness all came down to tiny chemicals in your brain? For decades, scientists have argued over the role of neurotransmitters in mental disorders. The idea is simple. Neurotransmitters are chemical messengers that carry signals between brain cells, and when they're imbalanced, things go wrong. Too little serotonin, and you might experience depression. Too much dopamine, and you could suffer from hallucinations. Mental health disorders, in this view, are largely biochemical problems, things that can, in theory, be fixed with medication. But not everyone agrees. Some researchers argue that reducing mental illness to just a chemical imbalance is far too simplistic. The brain is incredibly complex, and mental disorders involve a mix of genetics, environment, and life experiences. Studies have even shown that people with depression don't always have lower serotonin levels, raising questions about whether neurotransmitter imbalances are truly the root cause, or just a symptom of deeper issues. This debate has massive real-world consequences. If mental illness is just a chemical imbalance, then medication should be the perfect cure. But if the problem is more complex, rooted in trauma, neuroplasticity, or social factors, then relying solely on drugs might not be enough. So, do neurotransmitters really hold the key to understanding mental disorders, or have we oversimplified the brain's mysteries? And if we do find a perfect balance of chemicals, would that mean we could one day engineer perfect mental health? Memory formation. Your memories might be lying to you. We tend to think of memory as a mental video recorder, storing our past exactly as it happened, ready to be played back whenever we recall it. But science tells a very different story. Memories aren't stored like files in a computer. They're reconstructed, pieced together every time you remember them, and each time, details can change. This means that the memories you trust the most, the ones that feel the clearest, could be the most distorted. Memory formation is one of neuroscience's greatest mysteries. We know it involves neurons strengthening their connections, a process called synaptic plasticity. We also know that the hippocampus, a small seahorse-shaped structure in the brain, plays a crucial role in converting short-term memories into long-term ones. But beyond that, things get murky. Some researchers argue that memory is like a biological web, with new experiences constantly altering old ones. Others believe that memories might not be stored in a single place, but distributed throughout the brain, making them incredibly resilient and incredibly vulnerable to distortion. The controversy deepens when we look at memory manipulation. Studies show that false memories can be implanted. People can be made to vividly recall events that never happened. This has major implications for everything from eyewitness testimony to therapy and even personal identity. If our memories shape who we are, but they can be rewritten, what does that say about our sense of self? So, if memory is more fragile and unreliable than we think, how much of our past is real? And more importantly, if we had the power to edit our memories, would we use it? Role of genetics versus environment. Are you born to be who you are, or are you shaped by the world around you? This question has fueled one of the longest-running debates in science, nature versus nurture. Are intelligence, personality, and even success determined by genetics, or do environment and experience mold us into who we become? The answer is far from simple, and the debate is anything but settled. On one side, genetic determinists argue that DNA is the blueprint of our lives. Studies on identical twins who share the same DNA show striking similarities in intelligence, temperament, and even behaviors, even when raised apart. This suggests that genetics lay the foundation for much of who we are. Traits like height, eye color, and susceptibility to certain diseases are clearly inherited, so why not personality or intelligence? But on the other side, environmentalists push back. They argue that genes may set the stage, but experience writes the script. A child raised in a stimulating, supportive environment is far more likely to thrive than one raised in neglect, no matter their genetic potential. The impact of trauma, education, and culture all point to the massive role of environment in shaping individuals. Studies even show that early childhood experiences can alter gene expression, meaning nurture can modify nature at a fundamental level. So, where does that leave us? The truth likely lies somewhere in between. Genes may give us the ingredients, but the environment determines how the recipe turns out. But if that's the case, how much of who you are was truly your choice? Culture shaping behavior. What if your decisions, beliefs, and even emotions aren't entirely your own, but shaped by something much bigger than you? The idea that culture shapes behavior is both obvious and deeply controversial. From the way we speak and dress to the way we think about morality, success, or even happiness, culture acts like an invisible force molding us in ways we rarely question. But just how much does culture dictate human behavior? And how much free will do we really have? Consider individualistic versus collectivist cultures. In Western societies like the US and many European countries, personal success and independence are celebrated. You're expected to follow your dreams and stand out. But in many Eastern cultures, cooperation, family honor, and social harmony take priority over individual desires. Studies show that people raised in collectivist cultures are more likely to conform, while those from individualist cultures tend to challenge authority and take risks. Even something as simple as perception is influenced by culture. Research has shown that Westerners tend to focus on objects, while East Asians focus on the relationships between them. That means two people from different cultures could look at the same scene, but notice completely different things. So why is this controversial? Some argue that biology plays a bigger role than culture, pointing to human universals like emotions and survival instincts. Others argue that cultural conditioning is so strong that it can override even basic human tendencies, influencing everything from morality to cognitive biases. If culture shapes behavior this much, then what happens when cultures collide? Does globalization mean we are becoming more alike, or will cultural differences remain as strong as ever? And if we understand how culture shapes us, can we ever truly escape its influence? Safety of nuclear power. Nuclear power is either humanity's greatest energy solution or a ticking time bomb. It depends on who you ask. For decades, the debate over the safety of nuclear power has raged on, dividing scientists, policymakers, and the general public. On one side, nuclear energy is hailed as one of the cleanest, most efficient sources of power we have. Unlike fossil fuels, it doesn't pump carbon dioxide into the atmosphere. Unlike solar or wind, it provides a steady, uninterrupted power supply. But then, there's the other side. The disasters, the radiation, the terrifying images of Chernobyl and Fukushima. So which is it? A climate-friendly miracle, or a catastrophe waiting to happen? Advocates argue that modern nuclear reactors are incredibly safe compared to the early designs of the Cold War era. Fourth-generation reactors and small modular reactors are designed with passive safety features, meaning they can shut down automatically if something goes wrong. No human intervention needed. In fact, per unit of energy produced, nuclear power has caused fewer deaths than coal, oil, or even hydropower. But critics warn that even one meltdown can have devastating consequences. The Fukushima disaster in 2011, triggered by a tsunami, released radioactive material into the environment, causing mass evacuations and long-term health concerns. And then there's the issue of nuclear waste, highly radioactive material that remains dangerous for thousands of years. Where do we store it? And can we guarantee future generations will keep it contained? With the climate crisis escalating, some argue we can't afford to ignore nuclear energy. Others insist the risks are too great. So, is nuclear power the key to a sustainable future, or is it simply too dangerous to bet on? And if we don't embrace it, what's the alternative? Future of transportation. The way we move from place to place is on the verge of a revolution. but no one can agree on what comes next. Will we zip through cities in autonomous electric cars, fly across countries in hypersonic jets, or maybe even teleport? While that last one might still be science fiction, the future of transportation is a hotly debated topic with no clear answer. Some believe we're headed for a world of hyperloops and flying taxis, while others argue we're overhyping the possibilities and that real change is much further away than we think. One of the biggest ideas in transportation right now is electric and autonomous vehicles. Companies like Tesla and Waymo promise that self-driving cars will reduce accidents, ease traffic, and change urban landscapes. No more parking lots, no more traffic jams, just seamless, efficient transport. But skeptics point out that full autonomy is proving to be far more difficult than expected. The technology still struggles with unpredictable human drivers and ethical dilemmas, like how an AI should react in an unavoidable crash, raise serious concerns. Then there's high-speed transit. Elon Musk's Hyperloop concept proposes passengers shooting through vacuum tubes at over 600 miles per hour, cutting travel times drastically. Sounds great, except the physics, infrastructure costs, and safety concerns make many experts doubtful it will ever be widely implemented. Meanwhile, some say we should focus on high-speed rail, like Japan's bullet trains, proven technology that many countries still refuse to invest in. And let's not forget air travel. Supersonic jets are making a comeback, promising New York to London in under 4 hours. But with climate concerns growing, will air travel even be a viable long-term solution? With so many possibilities and limitations, the future of transportation is still up for debate. Will we finally break free from traffic and long commutes, or are we over-promising what's actually possible? Role of microbiota. Your body isn't just you, it's a thriving metropolis for trillions of microscopic organisms. And strangely enough, they might control way more than we ever imagined. For years, we thought bacteria were just disease-causing invaders. But now, scientists are discovering that the microbiota, the vast collection of bacteria, viruses, and fungi living inside us, might be one of the most important, yet overlooked factors in human health. Some researchers even suggest that these microbes influence everything from digestion to mood, immunity, and even brain function. But just how much power do they really have? The microbiota's role in digestion is well understood. These microscopic helpers break down food, synthesize vitamins, and regulate metabolism. But here's where things get weird. Some studies suggest they might also be affecting mental health. Experiments on mice have shown that transferring gut bacteria from an anxious mouse into a calm one can make the calm mouse anxious. If similar mechanisms apply to humans, it could mean gut bacteria are influencing depression, anxiety, and even personality traits. The controversy. Some scientists argue that the microbiome is overhyped. While its role in digestion is clear, the idea that gut bacteria might be steering thoughts and emotions is still unproven. The brain is vastly complex, and critics argue that microbiota research is still in its infancy, with many claims lacking solid evidence. If microbiota truly shape our bodies and minds, could we one day edit our microbial populations to boost mood, prevent disease, or even enhance intelligence? Or are we just scratching the surface of something far more complex than we realize? Function of sleep. You spend a third of your life unconscious. But why? For something so essential, sleep is still one of science's biggest mysteries. We know we need it. Go too long without it, and the brain starts shutting down. But what exactly is happening when we sleep? Why do we dream? And could we one day engineer a world where sleep is no longer necessary? One of the leading theories is that sleep acts as a biological reset button. It's when the brain clears out waste, consolidates memories, and repairs cells. But here's where things get strange. Scientists still don't fully agree on what sleep's most critical function actually is. Some believe it's mostly about memory consolidation, turning experiences into long-term knowledge. Others argue that sleep is mainly about removing toxins from the brain, preventing neurodegenerative diseases like Alzheimer's. And then there's the idea that sleep is simply an evolutionary leftover, an inefficient way for organisms to conserve energy. But some researchers are skeptical of these explanations. If sleep is purely about the brain, then why do even the simplest organisms sleep? Fruit flies, jellyfish, even worms experience sleep-like states, despite having no complex cognitive functions. Could it be something even deeper, a fundamental biological process we have yet to understand? Then comes the most controversial question. Could we hack sleep? If we could figure out exactly what makes sleep so essential, could we develop ways to replace it entirely? What would happen if humans no longer needed to sleep at all? Would we become more productive, or would our minds collapse without that nightly reset? Group selection. Could evolution favor the survival of the group rather than just the individual? For decades, the dominant idea in evolutionary biology has been natural selection at the level of individuals or genes. The selfish gene model, famously popularized by Richard Dawkins, argues that organisms behave in ways that maximize the survival of their own genetic material. But an alternative theory, group selection, suggests that sometimes evolution works at a higher level, favoring traits that benefit a group, even if they disadvantage an individual. The idea is simple. Imagine two competing groups. One is made up of selfless, cooperative individuals who work together for the common good. The other is full of selfish individuals who prioritize their own survival at the expense of the group. Even if selfish individuals within a group might outcompete their altruistic peers, the entire cooperative group could outcompete the selfish one. Over time, natural selection might favor groups with altruistic behavior, even if individuals within those groups don't directly benefit. But here's the controversy. Many scientists argue that group selection is unnecessary, that all forms of cooperation, from ants to humans, can be explained by kin selection and reciprocal altruism. In other words, we don't need to invoke group-level evolution because cooperative behaviors already help an individual's genes survive, either through relatives or strategic alliances. Yet, some evolutionary biologists, like E.O. Wilson, have pushed back. They argue that group selection could explain behaviors that gene-level selection struggles with, like extreme self-sacrifice, eusocial insects, and large-scale human cooperation. So, is evolution just selfish genes doing their thing, or does nature sometimes play the long game, shaping entire groups for survival? If group selection is real, it could redefine how we understand everything from human societies to the origins of morality itself. Role of mitochondria in aging. What if the secret to aging isn't in your DNA, but in tiny power plants inside your cells? For decades, scientists have searched for the cause of aging, why our bodies gradually break down over time. One leading theory points to an unexpected culprit: mitochondria. These microscopic structures are responsible for producing energy in almost every cell in your body. But as you age, they start to falter, and some researchers believe that this decline is what ultimately drives aging itself. Here's how it works. Mitochondria generate energy through a process called cellular respiration. But in doing so, they also produce free radicals, highly reactive molecules that damage cells, proteins, and even DNA. Over time, this oxidative stress accumulates, impairing mitochondrial function and triggering a cascade of cellular decline. The more damaged your mitochondria, the less energy your cells can produce, leading to everything from muscle loss to cognitive decline. But not everyone agrees that mitochondria are the main cause of aging. Some scientists argue that mitochondrial dysfunction is just a symptom of a larger process, not the root cause. Others believe that the body has natural repair mechanisms that counteract mitochondrial damage, and that aging is driven by a combination of genetic, metabolic, and environmental factors. Still, the mitochondrial theory of aging has fueled exciting research, including studies on mitochondria targeting drugs, calorie restriction, and even gene therapies designed to enhance mitochondrial function. If mitochondria truly hold the key to longevity, then understanding and possibly repairing them could lead to breakthroughs in anti-aging science. So, could reversing mitochondrial decline be the secret to a longer, healthier life? Or is aging far more complex than we realize? Altruism in evolution. If evolution is about survival of the fittest, why do we help each other, even at our own expense? In a world where natural selection is supposed to reward selfishness, altruism seems like a paradox. Why would an animal, or even a human, risk its own survival to help another? Shouldn't evolution favor those who put themselves first? Yet nature is full of acts of selflessness, from vampire bats sharing food with hungry roostmates, to meerkats standing guard against predators while the rest of the group eats. One possible explanation comes from kin selection, the idea that organisms are wired to help those who share their genes. If a mother sacrifices herself to save her offspring, her genetic lineage survives. This concept, championed by biologist William Hamilton, explains why altruism is most commonly seen in family groups. But what about acts of kindness between strangers? That's where reciprocal altruism comes in. Proposed by Robert Trivers, it suggests that animals, and humans, help others with the expectation that the favor will be returned later. Essentially, evolution might have favored cooperation because, in the long run, it benefits survival. But not everyone agrees. Some argue that true altruism, helping without any expectation of reward, shouldn't exist under natural selection. Others suggest that what looks like selflessness is actually a hidden form of self-interest, a way to build alliances or gain social status. So, is kindness just another survival strategy? Or is there something deeper at play, something evolution hasn't fully explained? If nature has programmed us to help others, does that mean morality itself is just an instinct? Possibility of extraterrestrial life. Are we alone in the universe, or is life out there waiting to be discovered? For decades, scientists, philosophers, and conspiracy theorists have debated the possibility of extraterrestrial life. Given the vastness of the universe, trillions of galaxies, each with billions of stars and even more planets, the idea that Earth is the only place where life has emerged seems, well, improbable. And yet, we have no definitive proof that life exists anywhere else. The theory of abiogenesis suggests that life arises from non-living matter when conditions are just right. If it happened here, why wouldn't it happen elsewhere? Scientists search for planets in the habitable zone where liquid water can exist, a key ingredient for life as we know it. And we've already found thousands of exoplanets, some eerily Earth-like. But then, there's the Fermi paradox, the unsettling contradiction between the high probability of alien life and the eerie silence of the cosmos. Where is everyone? Could it be that intelligent civilizations wipe themselves out before achieving interstellar travel? Or maybe they're out there but deliberately avoiding us. Some even suggest Earth is part of a cosmic zoo, observed but untouched. Some scientists, like Carl Sagan, believed we should listen and look for signals. Others argue that broadcasting our presence is reckless. What if the aliens we contact aren't friendly? So, is life out there, just waiting to be found? Or are we truly alone, a cosmic accident in an otherwise lifeless void? Until we get an answer, the question remains one of the greatest mysteries in science. Causes of mass extinctions. Mass extinctions have reshaped life on Earth over and over again. Could we be living in the next one? Earth has experienced at least 5 mass extinctions, each wiping out most species and resetting the course of evolution. The most famous, the asteroid that ended the dinosaurs. But while space rocks make for dramatic endings, they're not the only suspect in Earth's greatest die-offs. Some theories suggest that supervolcanoes played a major role. The Permian-Triassic extinction, often called the Great Dying, eliminated over 90% of marine species and 70% of land animals. The leading theory? Massive volcanic eruptions in what is now Siberia released so much carbon dioxide that it triggered runaway global warming, turning the planet into an unlivable hellscape. Others point to climate shifts, not just warming, but but cooling too. The Ordovician-Silurian extinction saw an ice age suddenly lock up ocean water, devastating marine life. Then, when the ice melted, sea levels surged, drowning coastal species. But some theories get even weirder. Could gamma-ray bursts, high-energy explosions from distant stars, have stripped away Earth's ozone layer, exposing life to lethal radiation? Could dark matter passing through our solar system have subtly disrupted orbits, leading to devastating cosmic events? And then there's today. Many scientists argue we're in the middle of a sixth mass extinction, driven not by asteroids or volcanoes, but by us. Deforestation, pollution, and climate change are pushing species to extinction at rates never seen before. So, what truly causes mass extinctions? Is it a single catastrophic event, or a slow, unavoidable cycle of planetary change? And if we are in the middle of one, how does it end? Punctuated equilibrium. What if evolution isn't slow and steady but happens in sudden bursts of chaos? For decades, scientists believed that evolution was a slow, gradual process, tiny changes accumulating over millions of years. But in the 1970s, paleontologists Niles Eldredge and Stephen Jay Gould proposed something radical. Evolution doesn't always creep forward, it jumps. They called it punctuated equilibrium. Instead of gradual change, this theory suggests that species stay mostly the same for long periods, with little evolution happening. Then, out of nowhere, boom! A rapid burst of evolutionary change occurs, creating new species in a short geological time span. Think of it like a pressure cooker. Things remain stable for a long time, but when the right conditions build up, transformation happens fast. Why is this idea so controversial? Because it challenges the traditional Darwinian view of slow, continuous evolution. Some critics argue that the fossil record simply isn't complete enough, that gaps between species don't mean evolution happens in bursts, just that we haven't found all the transitional forms yet. Others worry that punctuated equilibrium oversimplifies evolution, downplaying the role of natural selection over time. But there's strong support for the idea too. Fossil evidence shows that many species appear suddenly in the geological record, with little sign of gradual change. Some biologists believe this makes sense. Big evolutionary shifts could be triggered by environmental crises, genetic mutations, or sudden ecological opportunities. So, is evolution a smooth climb, or a series of sudden leaps? If punctuated equilibrium is correct, it means evolution isn't just about who survives, but when the world changes fast enough to force transformation. Role of sexual selection. Why do peacocks have ridiculous tails? Why do some animals evolve traits that seem more like a burden than a survival advantage? According to Charles Darwin, it's because natural selection isn't the only game in town. There's another force at play, sexual selection, and it has been shaping life on Earth just as much as survival of the fittest. The idea is simple but powerful. Some traits don't make an animal better at surviving, but they do make them better at attracting mates. The peacock's tail? Useless for escaping predators, but irresistible to peahens. The antlers of a stag? Not great for running through a forest, but essential for winning battles against rivals. In the world of sexual selection, the prize isn't just survival, it's reproduction. But here's where things get controversial. Some scientists argue that sexual selection explains far more than just flashy feathers and courtship dances. It could also be a driving force behind intelligence, creativity, and even human behaviors like humor and artistic ability. Some researchers believe that traits like music, storytelling, and abstract thinking evolved not because they helped us hunt or gather food, but because they made us more attractive to potential mates. However, not everyone buys into this idea. Critics argue that sexual selection can't fully explain why certain traits persist, especially when they seem impractical or costly. Others point out that in some species, mate choice doesn't follow a simple pattern. Sometimes, luck and circumstance matter more than biological traits. If sexual selection is truly as powerful as some believe, it means evolution isn't just about survival of the fittest, it's about survival of the most desirable. But that raises an even bigger question. What does that mean for humans? Are our cultures, behaviors, and even intelligence shaped by ancient mating strategies? And if so, how much of what we value is actually just evolutionary peacocking? Classification of viruses. Are viruses alive? That question alone has fueled one of the biggest debates in biology. Unlike bacteria or fungi, viruses don't eat, don't grow, and don't breathe. But they do invade living cells, hijack their machinery, and replicate with ruthless efficiency. So, what exactly are they? And more importantly, how do we classify them? At first glance, viruses look like the ultimate freeloaders. Tiny genetic code wrapped in a protein shell, incapable of doing anything on their own. They can't reproduce without a host, which is why some scientists argue they aren't even living organisms. Life, after all, is supposed to be self-sustaining. But here's where things get messy. Viruses evolve, they mutate, and they can even swap genes with other organisms. That sounds a lot like life, doesn't it? Scientists have tried to sort viruses into neat biological categories, but there's a problem. They don't fit anywhere. The classical tree of life includes bacteria, archaea, and eukaryotes. Viruses? They don't have a branch. Some propose a fourth domain of life, a separate category for viruses entirely. Others argue that viruses might have once been cells that lost the ability to function on their own, turning into genetic parasites over time. Then there's another possibility. What if viruses came before life as we know it? Some theories suggest viruses may have been the original genetic fragments that helped jumpstart evolution itself. If true, that would mean viruses aren't just strange biological parasites. They could be the missing link to understanding how life began. So, should we redefine what it means to be alive? Or are viruses something else entirely? A biological anomaly that doesn't need to play by the rules? Role of epigenetics in evolution. For decades, we thought evolution was all about random mutations and survival of the fittest, a slow, generational process driven by changes in DNA. But what if evolution isn't just about genes? What if your experiences, what you eat, how you live, even the stress you endure, could be passed down to your children and shape their biology? This is the radical idea behind epigenetics, and it's rewriting what we thought we knew about evolution. Epigenetics doesn't change the genetic code itself. Instead, it acts like a dimmer switch, turning genes on or off based on environmental influences. Imagine two identical twins, same DNA, same blueprint. One experiences famine, the other doesn't. Years later, the twin who endured starvation might pass down altered gene expression to their children, making them more prone to storing fat. The DNA stays the same, but the way it's read and expressed is different. This idea is controversial because it challenges traditional Darwinian evolution. The standard model says evolution happens through random mutations over millions of years, but epigenetics suggests organisms can adapt much faster within a single lifetime and pass those adaptations to their offspring. Some scientists argue this is a modern update to Lamarck's theory, the idea that acquired traits can be inherited, which was largely dismissed for over a century. If epigenetics plays a bigger role in evolution than we thought, it raises a profound question. Are we shaping our own evolutionary path through our choices and environment? And if so, how much control do we really have over our biological future? Nature of the vacuum of space, emptiness, nothingness, a vast sea of absolute void. But what if I told you that the vacuum isn't empty at all? What if, instead of being a dead, silent abyss, space is teeming with energy, quantum fluctuations, and virtual particles constantly winking in and out of existence? This is the mystery of the vacuum, and it's one of the most controversial questions in modern physics. In classical physics, a vacuum is simply the absence of matter, a place where no particles, no air, no anything exists. But quantum mechanics tells a different story. Even in the emptiest parts of the universe, space itself is alive with fleeting bursts of energy, known as quantum fluctuations. These fluctuations create virtual particles, tiny entities that pop into existence for a fraction of a second before disappearing again. This isn't just a theoretical idea, it's been observed. The Casimir effect, for instance, shows that empty space can exert a force on objects, and vacuum energy, the so-called zero-point energy, is even thought to play a role in the expansion of the universe. But this leads to a huge problem. If the vacuum is full of energy, why isn't the universe collapsing under its own weight? The vacuum energy predicted by quantum mechanics is 120 orders of magnitude higher than what we observe. That's a number so absurd, it's been called the worst prediction in physics. So, what is the vacuum really? Is it a quantum sea of infinite energy? A hidden layer of reality we don't yet understand? Or something even stranger? If empty space isn't actually empty, then what is it? Arrow of time. Time only moves forward. You age. You remember the past, but not the future. And no matter how much you wish otherwise, a broken egg never unbreaks. But why? The fundamental laws of physics don't actually require time to have a direction. So what forces time to march forward, never backward? This is the mystery of the arrow of time, one of the most puzzling questions in physics. At the core of this mystery is the second law of thermodynamics, which states that entropy always increases. Entropy is a measure of disorder, and the universe, it seems, is always moving toward more chaos. Ice melts, stars burn out, and everything decays. This is the closest thing physics has to a rule that gives time a direction. The past is orderly, the future is messy. But here's the problem. The laws of physics work just as well in reverse. If you filmed an atom bouncing around, then played it backward, it would still obey all the known equations of motion. So why doesn't the universe behave like this on a larger scale? Why don't we see shattered glass reassemble or spilled coffee leap back into the cup? One explanation is that the Big Bang set the universe in an extremely low entropy state, like a neatly stacked deck of cards. Over time, disorder has increased, creating the illusion of time flowing forward. But this raises another question. Why did the Big Bang start in such an ordered state to begin with? And could time ever run backward under the right conditions? Some physicists speculate that in a distant, contracting universe, time could reverse, creating a mirror reality where everything runs backward. If that's true, then time isn't a fundamental force, it's just an effect of entropy. And if entropy could be controlled, could time be manipulated too? Cosmological multiverse. What if the universe isn't the only one? What if beyond the limits of what we can see, there are countless other universes, each with its own galaxies, laws of physics, and maybe even alternate versions of you? This is the idea behind the cosmological multiverse, a theory that suggests our universe is just one of many, part of a vast, ever-expanding cosmic landscape. The idea stems from cosmic inflation, the rapid expansion that took place moments after the Big Bang. Some physicists, like Alan Guth and Andre Linde, propose that inflation didn't just create our universe, it never stopped, continuing to spawn new universes forever. Each universe, or bubble, could have different physical constants, meaning the laws of nature we take for granted, like gravity or electromagnetism, might work completely differently elsewhere. But here's where things get controversial. There's no direct evidence. The multiverse isn't something we can observe, measure, or test, which raises a huge question. Is it even science? Critics argue that without experimental proof, the multiverse is nothing more than philosophical speculation dressed up in physics. Others counter that if inflation theory is correct, and much of modern cosmology relies on it, then the multiverse is an unavoidable consequence. If true, it would change everything. It could explain why our universe seems so perfectly fine-tuned for life, because in an infinite multiverse, there would naturally be some universes where conditions are just right. But if we can never interact with these other realities, does it really matter? Is the multiverse a profound scientific breakthrough waiting to be understood, or just an escape hatch for ideas we can't explain? Until we find evidence, the answer remains beyond our universe, and maybe beyond our reach. Plate tectonics. The ground beneath your feet is moving. Not fast enough to notice, but slowly, relentlessly, reshaping continents, raising mountains, and tearing open oceans. This is plate tectonics, the unceasing motion of Earth's crust that explains why earthquakes shake cities, why volcanoes erupt, and why entire landmasses drift apart over millions of years. But for a long time, scientists dismissed this idea as pure nonsense. Before the 20th century, the continents were believed to be fixed in place. Then came Alfred Wegener, a German meteorologist, who noticed something odd. The coastlines of South America and Africa fit together like puzzle pieces. He proposed that continents weren't fixed at all, but drifted across the Earth's surface over time. His idea, called continental drift, was ridiculed. He had no explanation for how massive landmasses could move. It just didn't seem possible. Decades later, under the ocean, geologists discovered mid-ocean ridges, huge underwater mountain chains where new crust was forming. As molten rock rose from beneath, it pushed old crust away, slowly driving the continents apart. This discovery confirmed what Wegener had theorized all along. The Earth's surface wasn't fixed, it was broken into giant plates, constantly shifting and colliding. But not everyone accepted it immediately. Some scientists argued that if plates are always moving, why isn't the Earth ripping itself apart? Others questioned whether subduction, where one plate sinks beneath another, could actually recycle crust fast enough to balance the process. Even today, there are debates about what drives the movement of these plates. Is it the heat from Earth's core, or something even deeper? Plate tectonics explains earthquakes, volcanoes, and even the rise and fall of ancient supercontinents. But if Earth's crust is always shifting, what does that mean for our future? Could entire continents one day collide again, forming a new supercontinent? And if so, what will the world look like millions of years from now? Origin of the moon. Look up at the night sky and you'll see it. The moon, Earth's closest companion. But have you ever wondered where it actually came from? For something that's been around for over 4 billion years, its origin remains one of the most debated mysteries in science. For decades, scientists have tried to piece together the moon's origin story, but no single explanation fits perfectly. Some early theories suggested it simply formed alongside Earth, from the same swirling cloud of dust and gas. Others argued that Earth captured the moon, pulling in a wandering rock from space. The problem? Neither fully explains why the moon's composition is eerily similar to Earth's crust, yet missing certain elements. Then came the giant impact hypothesis, now the leading theory. According to this idea, around 4.5 billion years ago, a Mars-sized planet, Theia, crashed into the young Earth. The collision was so violent that molten rock and debris were blasted into space, eventually coalescing to form the moon. This explains why the moon shares Earth's chemistry, but with key differences. Volatile elements were likely burned off in the fiery impact. But even this widely accepted theory has problems. Some scientists argue that if Theia truly existed, why haven't we found distinct chemical traces of it? Others suggest alternative ideas, like the moon forming from multiple smaller impacts, or even being spun out of Earth itself due to extreme rotation. A theory once favored, but now largely dismissed. No matter which theory turns out to be right, the moon's origin is more than just a cosmic curiosity. It could hold the key to understanding Earth's past, and even the formation of other planets. So, was it an impact, a cosmic accident, or something we haven't even thought of yet? The answer may be waiting on the moon itself. Mechanisms of photosynthesis. Without photosynthesis, life as we know it wouldn't exist. Every breath of oxygen, every bite of food, every towering tree, all of it depends on this biological magic trick that turns sunlight into energy. But here's the catch. We still don't fully understand how it works. Sure, we know the basics. Plants take in carbon dioxide and water, use sunlight to trigger a series of chemical reactions, and release oxygen while producing glucose. Simple enough, right? Not even close. The molecular machinery inside plants is mind-bogglingly complex, operating with near-perfect efficiency, far beyond anything human engineers have ever built. And here's where the real controversy starts. For years, scientists believed that photosynthesis followed a straightforward step-by-step pathway. Light gets absorbed, energy gets transferred, and chemical bonds get formed. But recent discoveries suggest that quantum mechanics may be at play. Some studies indicate that plant cells don't just transfer energy like a baton in a relay race. They may use quantum superposition to explore multiple pathways at once, choosing the most efficient route. If true, this would mean that plants have unknowingly been harnessing the bizarre rules of quantum physics for billions of years. Not everyone is convinced. Skeptics argue that quantum effects are too delicate to survive in the messy, warm environment of a living cell. Others insist that classical physics alone is enough to explain photosynthesis, without the need for exotic quantum phenomena. The debate continues, with experiments pushing the limits of what we thought plants were capable of. If we could unlock the full potential of photosynthesis, we could revolutionize energy production, perhaps even creating artificial leaves that could power entire cities. But before we get there, one question remains. Have plants mastered physics in ways we're only beginning to understand? Quantum effects in chemistry. Most of us think of chemistry as predictable. You mix two chemicals, and they react. Simple. But what if I told you that some of the most important chemical reactions might be happening because of quantum physics? That at the tiniest scales, the world of molecules isn't as straightforward as it seems. This idea that quantum effects play a fundamental role in chemistry is both fascinating and controversial. Traditional chemistry operates on the laws of classical physics. It explains how atoms bond, how reactions occur, and how energy moves through molecules. But at extremely small scales, things start to get weird. Particles don't behave like tiny billiard balls. They behave like waves, existing in multiple places at once, tunneling through barriers they shouldn't be able to cross, and even choosing the most efficient reaction pathways as if they knew the best route in advance. One of the most intriguing examples of this is enzyme catalysis, the process that speeds up chemical reactions inside your body. Some researchers believe that enzymes might be using quantum tunneling, a bizarre phenomenon where particles slip through energy barriers instead of climbing over them. If true, this means your body's chemistry relies on quantum tricks to function efficiently. And then there's photosynthesis. Some experiments suggest that the way plants transfer energy might involve quantum coherence, where energy exists in multiple states at once, finding the quickest route to the reaction center. If plants are secretly quantum physicists, what else in nature might be using these effects? Of course, skeptics argue that biological systems are too chaotic, too warm for delicate quantum phenomena to survive. They believe classical physics alone can explain chemistry. But the more we study these effects, the more we realize nature might be playing by quantum rules in ways we never imagined. If quantum mechanics is deeply embedded in chemistry, it could redefine how we think about everything from drug design to renewable energy. But the real question is, if life itself is quantum, what else are we missing? Nature of chemical bonding. What if I told you that the very glue holding the universe together, chemical bonds, is still not fully understood? You'd think that by now we'd have figured out exactly how atoms stick together, right? Well, not quite. The nature of chemical bonding remains one of the most debated and mysterious topics in chemistry. At first glance, chemical bonds seem simple. Atoms share, steal, or swap electrons, forming stable molecules. This is what we were all taught in school. Ionic bonds involve electron theft, covalent bonds involve sharing, and metallic bonds create electron seas. Case closed, right? Not exactly. Take covalent bonding, a fundamental concept. Traditional chemistry says atoms share electrons to form stable pairs, but quantum mechanics throws a wrench into this explanation. Electrons don't orbit like tiny planets. they exist in fuzzy probability clouds. In reality, when two atoms bond, their electrons don't just pair up in a straightforward way. They enter a strange quantum superposition where they are spread out over both atoms at once. So, do molecules even have bonds in a classical sense, or are they just complex quantum interactions? And then there's the mystery of the hydrogen bond. This weak attraction between molecules is responsible for everything from water's unique properties to the structure of DNA. But is it even a bond at all? Some scientists argue it's more of an electrostatic force, while others believe quantum tunneling and entanglement may be playing a role. These questions aren't just theoretical. Understanding chemical bonding at a deeper level could revolutionize materials science, nanotechnology, and even drug design. The problem? We still don't have a unified theory that fully explains all types of bonding in every situation. So what if our entire understanding of how matter holds together is incomplete? What else might we be missing? Existence of black holes. Black holes shouldn't exist, at least not according to common sense. Imagine an object so dense, so powerful that not even light, the fastest thing in the universe, can escape its grasp. It sounds more like a cosmic horror story than real physics. And yet, black holes are one of the most fascinating and controversial topics in science. The idea of black holes first emerged from Einstein's general relativity. His equations suggested that if enough mass is packed into a small enough space, gravity would become so intense that it would create a one-way exit from the universe. But even Einstein himself was skeptical. He thought nature wouldn't allow such extreme objects to exist. Fast forward a century, and we now have mountains of evidence suggesting they are real. We've seen the effects of black holes on surrounding stars, detected gravitational waves from their collisions, and even captured the first ever image of one, a glowing ring of light surrounding a cosmic abyss. But here's where it gets weird. Do we truly know what's inside a black hole? Current physics says the core collapses into a singularity, a point of infinite density where all known laws of physics break down. But that's a problem. Infinite density makes no sense. Some scientists argue that black holes might not be what we think they are. Could they be wormholes, cosmic holograms, or something even stranger? Hawking's famous black hole information paradox suggests that these objects might be destroying information, something that violates fundamental laws of quantum mechanics. If black holes aren't what we think, then what are they? And if they do break physics, does that mean our entire understanding of the universe needs to be rewritten? Kuiper Belt and Oort cloud. Beyond Neptune lies a cosmic graveyard, an icy wasteland of forgotten worlds and ancient relics from the birth of the solar system. This is the Kuiper Belt, a region teeming with frozen debris, dwarf planets, and possibly answers to some of the biggest mysteries in astronomy. But if you go even farther, past the reach of our telescopes, you enter the Oort cloud, a hypothetical shell of icy bodies that may be the birthplace of long-period comets. These two regions challenge everything we thought we knew about the structure of our solar system. The Kuiper Belt is real. We've seen it. It's home to Pluto, Eris, and countless other icy objects, remnants from the chaotic formation of our cosmic neighborhood. It's often compared to an asteroid belt, but it's far larger, extending up to 50 times the distance between Earth and the Sun. The Oort cloud, however, is different. It's purely theoretical. No one has ever directly observed it. Yet many scientists believe it must exist because comets like Halley's or Hale-Bopp had to come from somewhere beyond the Kuiper Belt. Here's where it gets interesting. If the Oort cloud is real, it could stretch up to a light year from the Sun, meaning the outer edges might be influenced by passing stars or even interstellar objects. Some researchers speculate that the Oort cloud might contain rogue planets, orphaned worlds flung out of their original systems, drifting in the dark. But there's another mystery lurking in the Kuiper Belt, something astronomers call Planet 9. Some strange gravitational effects suggest that a massive, hidden planet, several times the size of Earth, might be lurking out there, waiting to be found. If we ever confirm the Oort cloud's existence or find Planet 9, it could completely reshape our understanding of the solar system. But until then, the outer reaches of our cosmic backyard remain an unsolved enigma, silently orbiting in the frozen dark. Nature of gamma-ray bursts. If Earth were unlucky enough to be in the path of a gamma-ray burst, civilization could be wiped out in seconds. These are the most powerful explosions in the universe, unleashing more energy in a few moments than the sun will in its entire lifetime. But what exactly causes them? And could one ever be aimed at us? Gamma-ray bursts, or GRBs, were first discovered by accident in the 1960s. During the Cold War, US satellites designed to detect nuclear explosions started picking up mysterious flashes of high-energy radiation from deep space. At first, the source was unknown, and for decades, scientists debated whether these were the signatures of exotic supernovae, colliding neutron stars, or something even stranger. Today, the leading theories suggest that there are two main types of gamma-ray bursts. The long-duration bursts, lasting more than 2 seconds, likely come from massive stars collapsing into black holes. The short bursts, lasting just milliseconds, are thought to be the result of neutron stars or black holes merging. Both events produce incredibly focused jets of energy that, if aimed directly at Earth, could sterilize entire planets. The controversy. We still don't fully understand them. Some bursts behave in ways that don't fit current models, leading some physicists to speculate that unknown physics, perhaps even exotic dark matter interactions, could be involved. Others wonder if some GRBs could be artificially created, a terrifying prospect that hints at the existence of ultra-advanced civilizations. Could a gamma-ray burst ever hit Earth? So far, no direct threats have been detected, but if one did, it could cause a mass extinction event worse than the asteroid that wiped out the dinosaurs. So, are we safe? Or is the universe hiding a cosmic sniper, waiting to fire? Dark matter halos. Galaxies are spinning too fast. Based on what we know about gravity, many of them should have torn themselves apart long ago. But they haven't. Something invisible is holding them together. That something is what we call dark matter halos. Massive, unseen structures that act as cosmic scaffolding, shaping galaxies and even the universe itself. Unlike regular matter, dark matter doesn't emit, absorb, or reflect light, making it impossible to see directly. Yet its gravitational influence is undeniable. Galaxies move as if they are embedded in vast, spherical halos of dark matter, far larger than the galaxies themselves. These halos are thought to be the cosmic glue that keeps galaxies from flying apart, explaining discrepancies in their motion that ordinary physics can't account for. But here's the controversy. We still have no idea what dark matter actually is. The leading theories suggest it could be made up of exotic particles like WIMPs, weakly interacting massive particles, or axions, ghostly entities that barely interact with normal matter. Others argue that dark matter doesn't exist at all, and instead, we need to modify our understanding of gravity itself. A theory called modified Newtonian dynamics, MOND, suggests that gravity behaves differently at galactic scales, eliminating the need for dark matter altogether. So, are dark matter halos the invisible architects of the cosmos, or are we fundamentally misunderstanding how gravity works? If dark matter exists, finding it could revolutionize physics. If it doesn't, then the laws of the universe may need to be rewritten. Which possibility is more unsettling? Interstellar medium, space is not empty. It may look like a vast, silent void, but in reality, it's filled with an invisible, ever-changing substance known as the interstellar medium, a mix of gas, dust, and charged particles stretching between the stars. Without it, galaxies wouldn't exist, stars wouldn't form, and the universe as we know it would be drastically different. The interstellar medium, or ISM, is often called the cosmic nursery because it's the birthplace of new stars. Clumps of gas collapse under gravity, forming glowing new suns, while leftover material drifts through space, waiting for its turn to create something new. But this interstellar soup is also responsible for something far more mysterious: the way galaxies evolve over billions of years. Here's where things get controversial. The ISM is full of strange phenomena we still don't fully understand. It contains massive, unseen magnetic fields that seem to influence the motion of gas clouds, yet we have no idea where they come from. Some scientists argue that dark matter interacts with the ISM in ways we haven't detected. Others suggest that cosmic rays, high-energy particles speeding through space, shape the interstellar medium in ways that defy our current physics models. Even more puzzling is how the ISM affects star death. Supernova, massive star explosions, send shockwaves through this medium, triggering more star formation. But some researchers believe these explosions can halt star birth instead, choking off galaxies from making new stars altogether. So, is the interstellar medium a cosmic life-giver, a silent killer, or both? Its effects are so complex that we're still piecing the puzzle together. But one thing is certain: space is far from empty. The real question is, what else is hiding in the invisible fabric between the stars? Mechanisms of star formation. Stars are born in chaos. Deep in the coldest, darkest regions of space, invisible clouds of gas and dust drift aimlessly for millions of years, until something disturbs them. A passing star, a collision of galaxies, or the shockwave of a distant supernova sends ripples through space, compressing the cloud, igniting a slow but inevitable chain reaction. And just like that, a new star begins to form. But here's where things get complicated. While we understand the general process, the exact mechanisms of star formation are still a subject of debate. Gravity pulls the gas together, heating it up until nuclear fusion ignites. But why do some clouds collapse into massive stars, while others barely manage to spark? Why do some regions of space form clusters of stars, while others remain barren? These are questions astrophysicists are still struggling to answer. One of the biggest mysteries is turbulence. Gas clouds in space aren't just floating serenely, they're chaotic, moving in unpredictable patterns. Some theories suggest that turbulence plays a major role in determining which clouds will collapse and which won't. Others argue that magnetic fields threading through these clouds resist collapse, slowing down the process. In fact, some scientists believe that without magnetic forces, stars would form much faster, perhaps too fast for galaxies to sustain themselves. Another controversy? The role of dark matter. Some researchers suggest that unseen dark matter clumps could act as gravitational anchors, pulling gas together and triggering starbirth. If true, this would mean star formation isn't just a process of normal matter, but is intimately tied to one of the greatest cosmic mysteries of all time. Despite these debates, one thing is certain: without star formation, the universe would be nothing but a cold, lifeless void. Every planet, every element, every living thing owes its existence to a cloud of gas that collapsed billions of years ago. But if the exact rules of star formation are still unclear, how many other cosmic processes are we still completely in the dark about? Origin of the solar system. The solar system didn't just appear, it had to be built. But how do you take a cloud of dust and gas floating in space and turn it into planets, moons, and an entire star system? Scientists think they have the answer, but the details of how it all happened are still up for debate. The most widely accepted theory is the nebula hypothesis. Around 4.6 billion years ago, a massive cloud of gas and dust, left over from previous generations of stars, collapsed under its own gravity. As it shrank, it started spinning faster, flattening into a swirling disk with a dense, hot center. That center ignited, forming the sun, while the remaining material clumped together to create planets, moons, asteroids, and everything else in our solar system. Sounds simple, right? Not exactly. There are some problems. Why do some planets have weird orbits? Why did the gas giants, Jupiter and Saturn, form so far from the sun, while rocky planets like Earth and Mars stayed close? And what about the late heavy bombardment? a period when massive asteroids rained down on the planets. Some scientists think it was caused by Jupiter and Saturn shifting their orbits, disrupting everything in their path. But others argue this event may not have even happened at all. Then there's the question of how the gas giants formed so quickly. Standard models suggest they needed millions of years to collect enough material, but recent evidence suggests they may have formed in just a few thousand years, far too fast for conventional theories to explain. While we've pieced together a rough timeline, the finer details remain a mystery. And if we still don't fully understand how our own solar system formed, how can we be sure we truly understand the process in exoplanetary systems across the universe? Safety and efficacy of vaccines. Vaccines are one of the greatest medical achievements in human history, credited with saving millions of lives and eradicating deadly diseases. And yet, they remain one of the most hotly debated topics in modern science. How can something so essential also be so controversial? The science behind vaccines is simple but brilliant. By exposing the body to a weakened or inactive form of a virus, the immune system learns how to fight it off without actually getting sick. This prepares the body for the real thing, making infections far less severe or preventing them altogether. Smallpox, a disease that once killed millions, was wiped out entirely because of vaccines. Polio, which used to paralyze children worldwide, is now incredibly rare. But despite their success, vaccines have also been the subject of intense skepticism. Some concerns stem from historical failures, like the Qatar incident in 1955, where improperly inactivated polio vaccines caused infections instead of preventing them. Others come from a now debunked 1998 study falsely linking vaccines to autism, a claim that spread like wildfire despite being completely discredited. The debate isn't just about science, it's about trust. Some argue that pharmaceutical companies and governments haven't been transparent enough, fueling suspicion. Others worry about rare side effects, even though the risks of vaccines are statistically far smaller than the diseases they prevent. And then there's the question of herd immunity. Should vaccination be a personal choice or a public responsibility? At its core, the controversy over vaccines isn't just about medicine. It's about how we weigh risk, trust science, and make decisions for society as a whole. And as new diseases emerge, one question remains. Can we afford to ignore a tool that has saved so many lives? Origin of the elements. Everything around you, the air you breathe, the water you drink, even your own body, is made from a collection of elements. But where did those elements come from? Why does the universe have hydrogen, carbon, gold, and uranium instead of nothing at all? The answer is buried deep in the heart of stars, supernovae, and the very fabric of the cosmos itself. Scientists believe that the elements were forged in a sequence of violent, universe-shaping events. The lightest elements, hydrogen and helium, were born moments after the Big Bang, but the heavier ones, the oxygen in your lungs, the iron in your blood, the gold in your jewelry, came from something far more extreme: the death of stars. Inside the cores of massive stars, atoms smash together, fusing into heavier elements. When those stars explode as supernovae, they scatter these elements across space, seeding the universe with the building blocks of planets, life, and everything we know. But not everyone agrees on the exact details. Some physicists argue that neutron-star collisions, not just supernovae, played a key role in producing the heaviest elements like gold and platinum. Others suggest that the conditions for element formation might have been different in the early universe than we assume. Could unknown physics have shaped the periodic table in ways we still don't understand? This mystery is far from settled, and new discoveries keep challenging our assumptions. What if there are entirely different cosmic processes producing elements we haven't even considered? If the periodic table is our cosmic recipe book, we're still trying to figure out exactly how the universe wrote it. Origin of the cosmic microwave background. There's an invisible whisper from the birth of the universe, stretching across the entire cosmos. A faint, persistent signal that exists everywhere, all the time. It's not coming from stars, black holes, or galaxies. It's coming from the very beginning of time itself. This is the cosmic microwave background, CMB, and it might be the most important clue we have about the origins of the universe. The CMB is often described as the afterglow of the Big Bang, the remnant heat from a time when the universe was just a hot, dense soup of particles. About 380,000 years after the Big Bang, the universe cooled enough for atoms to form, allowing light to travel freely for the first time. That light has been stretching and cooling ever since, eventually becoming the faint microwave radiation we detect today. This discovery was a game changer. In 1964, scientists Arno Penzias and Robert Wilson accidentally stumbled upon this signal while trying to eliminate interference from their radio telescope. Instead of noise, they had uncovered the oldest light in the universe, confirming key predictions of the Big Bang model. But here's where things get controversial. While most cosmologists accept the CMB as definitive evidence of the Big Bang, some dissenters argue that alternative theories, like the steady-state theory or cyclic universe models, could explain the data differently. Others debate whether unexplained anomalies in the CMB, like the so-called cold spot, hint at new physics or even parallel universes. So, is the cosmic microwave background the final proof of the Big Bang, or is it hiding something even more profound? If this is the universe's oldest signal, what else could it be telling us about reality itself? Existence of a molten core. Beneath your feet, just a few thousand kilometers down, lies a world of molten rock and searing metal, a vast, churning ocean of liquid iron that keeps our planet alive. At least, that's what most scientists believe. The existence of Earth's molten core is one of the most widely accepted ideas in geology, but here's the catch. No one has ever seen it. Unlike the surface of the moon, or even the depths of the ocean, we've never drilled deep enough to directly observe the core. The deepest hole ever drilled, the Kola Superdeep borehole, only scratched about 12 kilometers down, just 0.2% of the way to the center. Everything we know about Earth's interior comes from indirect clues, like seismic waves, magnetic fields, and computer models. Seismic data provides our strongest evidence. When earthquakes happen, they send shock waves rippling through the planet. Some waves can pass through liquid, while others can't, creating a pattern that suggests a solid inner core surrounded by a molten outer core. This dynamic system is believed to generate Earth's magnetic field, shielding us from deadly cosmic radiation. Without it, life as we know it wouldn't exist. But not everyone is convinced. Some alternative theories propose that Earth's core might not be as molten as we think, or that different materials, perhaps even exotic, unknown substances, exist deep inside. Others question whether we fully understand how Earth's magnetic field is generated, suggesting that new discoveries could rewrite what we think we know. If Earth's core is more complex than we imagined, what else might be hidden beneath the surface? Is our planet's heart still a mystery waiting to be unraveled, or have we been staring at the answer all along? Mechanisms of enzyme catalysis. Your body is a high-speed biochemical factory where millions of reactions happen every second. But here's the mystery. Most of these reactions should take thousands, even millions of years to occur naturally. And yet they happen almost instantly. How? The answer lies in one of nature's greatest tricks: enzymes, tiny biological machines that speed up reactions with near magical precision. At the core of this mystery is enzyme catalysis, the process by which enzymes accelerate chemical reactions. The traditional explanation follows the lock and key model, where the enzyme and its target molecule fit together perfectly. But things get strange when we dive deeper. For decades, scientists believed enzymes worked simply by stabilizing molecules and lowering the activation energy needed for reactions. But modern research suggests something even more bizarre. Enzymes may actually manipulate quantum mechanics to get the job done. Some experiments suggest that enzymes enable quantum tunneling, where particles skip over energy barriers instead of climbing them. This would mean that enzymes don't just speed up reactions, they bend the rules of classical chemistry. Not everyone agrees with this idea. Some researchers argue that more conventional physics, such as electrostatic interactions, fully explain enzyme efficiency. Others believe that enzyme evolution itself has fine-tuned them to exploit quantum effects, making them far more sophisticated than we ever imagined. If quantum tunneling is truly at play, it could reshape how we understand not just biology, but chemistry itself. Could the secrets of enzyme catalysis one day help us design super-efficient artificial enzymes or unlock new frontiers in medicine? Or are we still missing something even bigger? Stability of certain elements. Some elements are like ticking time bombs, constantly breaking apart, while others sit calmly, unchanged for billions of years. But why? What makes some elements stable while others collapse in an instant? This question has led to one of the biggest mysteries in nuclear physics, the island of stability. In the periodic table, most elements beyond uranium are radioactive, meaning their atoms decay over time, sometimes in mere fractions of a second. The heavier an element gets, the more unstable it tends to be. But physicists believe that certain super-heavy elements, ones we've never even seen in nature, might be strangely stable, lasting seconds, minutes, or even longer than the age of the universe. The idea comes from nuclear shell theory, which suggests that atomic nuclei have magic numbers of protons and neutrons that make them extra stable, just like how electrons fill energy levels in atoms. If a super-heavy element lands on this so-called island of stability, it might resist decay far longer than expected. But here's the problem. We've never been able to synthesize one stable enough to prove it. Some scientists believe we're close, pointing to recent discoveries of elements like moscovium and oganesson, which hint that stability may increase as we push further into uncharted atomic territory. Others argue that this island is a mirage. Perhaps these elements exist, but only fleetingly, with lifetimes too short to be useful. If we do find a long-lived super-heavy element, it could redefine chemistry and nuclear physics, opening doors to new materials, energy sources, or even undiscovered laws of nature. Could we one day engineer an element more stable than anything found on Earth? Or are we chasing an illusion, hoping to hold on to something that was never meant to last? Concept of aromaticity. Some molecules refuse to behave the way they should. Instead of following the normal rules of chemical bonding, they form strange, ultra-stable rings with electrons that seem to float around freely. This is the essence of aromaticity, one of the most puzzling and fundamental concepts in chemistry. The term might make you think of pleasant smells. After all, many aromatic compounds, like benzene, were originally discovered in fragrant substances. But scientifically, aromaticity is about stability. Unlike most molecules, which have fixed bonds between atoms, aromatic compounds share electrons across the entire ring structure, creating a weird cloud of electron density that makes them far more stable than expected. Here's where things get controversial. For decades, chemists believed that aromaticity followed a strict rule. A molecule must have a specific number of electrons in its ring, called Huckel's rule, to be aromatic. But then, anti-aromatic compounds were discovered, structures that should have been stable, but turned out to be highly reactive. Even more confusing, some molecules defied both categories, existing in a strange limbo between aromatic and non-aromatic states. Today, chemists debate whether aromaticity is even a binary property, or if it exists on a spectrum. Some molecules seem to switch between aromatic and non-aromatic states, while others challenge the very definition of what it means to be aromatic. Understanding aromaticity isn't just an academic exercise, it's the foundation of organic chemistry, materials science, and even pharmaceuticals. Could we one day manipulate aromaticity to create superstable materials or entirely new forms of chemistry? Or will we always be chasing a definition that refuses to be pinned down? Nature of chemical bonding. What if I told you that the very glue holding the universe together, chemical bonds, is still not fully understood? You'd think that by now we'd have figured out exactly how atoms stick together, right? Well, not quite. the nature of chemical bonding remains one of the most debated and mysterious topics in chemistry. At first glance, chemical bonds seem simple. Atoms share, steal, or swap electrons, forming stable molecules. This is what we were all taught in school. Ionic bonds involve electron theft, covalent bonds involve sharing, and metallic bonds create electron seas. Case closed, right? Not exactly. Take covalent bonding, a fundamental concept. Traditional chemistry says atoms share electrons to form stable pairs, but quantum mechanics throws a wrench into this explanation. Electrons don't orbit like tiny planets. They exist in fuzzy probability clouds. In reality, when two atoms bond, their electrons don't just pair up in a straightforward way. They enter a strange quantum superposition where they are spread out over both atoms at once. So, do molecules even have bonds in a classical sense, or are they just complex quantum interactions? And then there's the mystery of the hydrogen bond. This weak attraction between molecules is responsible for everything from water's unique properties to the structure of DNA. But is it even a bond at all? Some scientists argue it's more of an electrostatic force, while others believe quantum tunneling and entanglement may be playing a role. These questions aren't just theoretical. Understanding chemical bonding at a deeper level could revolutionize materials science, nanotechnology, and even drug design. The problem? We still don't have a unified theory that fully explains all types of bonding in every situation. So what if our entire understanding of how matter holds together is incomplete? What else might we be missing? Mechanisms of atmospheric chemistry. Earth's atmosphere is a vast, swirling chemical laboratory, constantly reacting, shifting, and reshaping the conditions that make life possible. But despite our deep understanding of chemistry, there's one thing scientists still debate. How exactly do the countless chemical reactions in the atmosphere work, and what forces are shaping them? At first glance, atmospheric chemistry seems straightforward. Sunlight breaks molecules apart, oxygen reacts with pollutants, and weather moves everything around. But when you zoom in, things get weird. The air we breathe is filled with radicals, highly reactive molecules that exist for mere fractions of a second before disappearing into new compounds. Some of these reactions create the ozone layer, shielding us from deadly radiation. Others form acid rain, corroding cities and forests. And some, like the interplay of carbon dioxide, methane, and aerosols, determine Earth's climate itself. One of the biggest debates in atmospheric chemistry is about how human activity influences these reactions. We know that emissions from factories and cars change air quality, but predicting exactly how new chemicals will interact in the atmosphere is a challenge. For instance, scientists once thought CFCs, chlorofluorocarbons, were harmless until they were found to be destroying the ozone layer. What other invisible dangers are we missing? Then there's the mystery of climate feedback loops. Do certain atmospheric reactions amplify warming or help cool the planet? And how much do natural processes, like volcanic eruptions or plant emissions, contribute compared to human-made pollutants? If we could fully decode the chemistry of our atmosphere, we might find ways to engineer cleaner air, prevent climate disasters, or even terraform other planets. But until then, the air around us remains an unpredictable, ever-changing puzzle, one we're still racing to solve. Existence of quasi-crystals. Crystals are supposed to follow rules, perfectly repeating patterns of atoms forming precise structures. But what if nature had been hiding a completely different kind of order, something that defied everything we thought we knew about solid matter? This is the strange world of quasi-crystals, materials that shouldn't exist, yet somehow do. For decades, scientists believed that all crystals had translational symmetry, meaning their atomic structures repeated predictably, like tiles on a bathroom floor. But in 1982, Israeli scientist Dan Shechtman discovered something that shattered this assumption. He found a material with an ordered atomic structure that never repeated, arranged in a way that was mathematically impossible, or so everyone thought. The discovery was met with ridicule. Crystallography textbooks stated with certainty that quasi-crystals couldn't exist. Schechtman was even laughed at by colleagues and told to go read a book on solid-state physics. For years, the scientific community rejected his findings, but as more researchers examined the evidence, they realized that Schechtman was right. In 2011, he won the Nobel Prize in Chemistry for proving that quasi-crystals were real. So why is this so controversial? Because it rewrote the fundamental understanding of solid matter. Quasi-crystals challenge the traditional definition of what a crystal even is. They also appear in unexpected places. Some have been found in meteorites, hinting that nature may have created them long before we did. Now, scientists are exploring how quasi-crystals could be used in everything from non-stick coatings to ultra-hard materials. But their existence still raises deeper questions. Are there other unknown forms of matter waiting to be discovered? What other impossible structures might nature be hiding from us? Molecular machines. Imagine machines so small that they could fit inside a single cell, repairing DNA, delivering drugs directly to diseased tissues, or even assembling molecules with atomic precision. These aren't science fiction. They're molecular machines, and they could revolutionize medicine, technology, and even the way we think about life itself. Molecular machines are nanoscale structures that move, rotate, and perform mechanical tasks, just like the gears and levers in a watch, except they operate at the scale of individual molecules. Some already exist in nature. Take ATP synthase, an enzyme found in cells that spins like a microscopic turbine to produce energy, or kinesin proteins, which literally walk along cellular highways, carrying vital cargo. But what if we could design and build our own molecular machines? Scientists are now developing synthetic versions, tiny molecular motors that can be controlled by light, electricity, or chemical reactions. In 2016, this work won the Nobel Prize in Chemistry, marking a huge leap toward a world where artificial molecular machines could be used for everything from targeted drug delivery to creating self-repairing materials. So why is this controversial? Because if we can engineer molecular machines, could we one day create self-replicating ones? The idea of nanobots multiplying uncontrollably inside the body or environment sparks both excitement and fear. Some researchers worry about unintended consequences, while others argue we are still far from that reality. But one thing is certain: molecular machines have already begun to blur the lines between biology and technology. Could we one day build a fully synthetic life form from scratch? If nature has spent billions of years perfecting molecular machines, how long will it take for us to catch up? Role of volcanism in climate. There's a force on Earth that has shaped entire continents, wiped out species, and even altered the course of human history, all without a single conscious thought. Volcanoes. They're not just fiery mountains. They might be one of the most powerful climate influences on the planet. Some scientists even argue that volcanic eruptions have played a bigger role in shaping Earth's climate than we ever realized. Volcanoes release massive amounts of gases and particles into the atmosphere. Some, like carbon dioxide, trap heat and contribute to global warming. Others, like sulfur dioxide, reflect sunlight and cause cooling. A single large eruption can lower global temperatures for years. The 1815 eruption of Mount Tambora in Indonesia was so massive that it triggered the year without a summer, plunging temperatures, ruining crops, and leading to widespread famine. But here's where the controversy begins. Some researchers believe volcanic activity has contributed to long-term climate change, even playing a role in past ice ages. Others argue that while individual eruptions can cause short-term cooling, their impact is insignificant compared to human-driven carbon emissions. The biggest debate? Whether modern climate change models properly account for volcanic influences. Some claim they overestimate the role of CO2 while underestimating volcanic effects. If volcanoes have altered climate before, could they do it again? And more importantly, could we one day harness this natural force, perhaps even trigger small eruptions to cool the planet intentionally? A wild idea, but considering how much power volcanoes already have, maybe nature has been running its own climate experiments all along. Future of ice sheets. The fate of the world's ice sheets could decide the future of civilization itself. These vast frozen landscapes hold enough water to reshape coastlines, drown cities, and alter global weather patterns in ways we're only beginning to understand. But just how much ice will melt, and how fast, remains one of the most controversial questions in climate science. Greenland and Antarctica contain 2/3 of the planet's fresh water, locked away as ice. If they were to melt completely, sea levels could rise by over 200 feet, turning major cities into underwater relics. But that's not the only concern. As ice sheets break apart, they disrupt ocean currents, affect weather systems, and even influence the Earth's rotation. The real debate lies in how quickly this process is unfolding. Some scientists argue that we've already passed the tipping point, with irreversible melting underway. The evidence? The collapse of ice shelves in Antarctica, the accelerating flow of glaciers, and the discovery that warming water is eating away at ice from below. Others believe there's still time, that the ice sheets are more resilient than we think, and that stabilizing global temperatures could slow or even halt their retreat. But here's the real question. What happens if we're wrong? If ice loss is faster than predicted, we could see catastrophic flooding within our lifetimes. Could we find a way to refreeze the poles, redirect ocean currents, or will future generations simply have to abandon the coasts and move inland? One thing is certain, the fate of our ice sheets isn't just a scientific mystery, it's a question of survival. Possibility of a supercontinent. Earth's continents are drifting, but where are they going? Right now, the continents are scattered across the globe, but geologists believe they are slowly moving toward a future supercontinent, one that could reshape life on Earth in ways we can barely imagine. This isn't just speculation, it has happened before. Hundreds of millions of years ago, all land on Earth was fused together in a massive supercontinent called Pangaea. Over time, it broke apart, creating the continents we know today. But plate tectonics never stops. Continents are constantly shifting, moving at about the same speed as your fingernails grow. And in another 200 to 300 million years, they could collide again, forming a new supercontinent. There are several competing models for what this might look like. One idea, called Pangaea Proxima, suggests that the continents could slowly drift back together into one massive landmass near the equator. Another, called Amasia, predicts that North America and Asia could merge at the North Pole. Meanwhile, the Nova Pangaea model envisions a completely new land arrangement, driven by changes in ocean currents and plate motion. But what would this mean for life on Earth? A supercontinent could drastically alter climate patterns, potentially creating vast deserts or extreme weather zones. It could also disrupt ocean currents, reshaping ecosystems, and possibly even triggering mass extinctions. Some scientists argue that predicting plate tectonics millions of years into the future is impossible due to the chaotic nature of the process. Others believe the models are solid, based on how the continents have behaved in the past. If Earth is heading toward another supercontinent, what will the world look like? Will it be a paradise of connected land masses, or a hostile environment of extreme conditions? And if humans are still around, will we adapt, or will we need to find another home? Causes of earthquakes. The ground beneath your feet is not as solid as it seems. In an instant, the Earth can shake violently, tearing apart cities, triggering tsunamis, and reshaping landscapes. But what actually causes earthquakes? And why do some scientists believe there's more to them than just shifting tectonic plates? The most widely accepted explanation is plate tectonics. The Earth's crust isn't a single solid shell. It's broken into massive pieces called tectonic plates that float on a layer of molten rock. As these plates move, they grind against each other, get stuck, and build up stress. When that stress finally releases, the result is an earthquake. Simple, right? Not always. Some researchers argue that not all earthquakes fit neatly into this model. For example, deep earthquakes, those occurring more than 300 miles below the surface, happen in areas where rock should be too hot and soft to store enough stress to rupture. Scientists suspect other forces may be at play, such as mineral transformations that release energy deep within the mantle. Then, there's the theory that earthquakes might not always be natural. Human activity, such as fracking, dam construction, and deep mining, has been linked to unexpected seismic activity. Some earthquakes have even occurred in places where tectonic movement isn't common. Could human actions be creating artificial fault lines? And here's where things get even stranger. Some researchers speculate that electromagnetic shifts or even solar activity might have subtle influences on earthquake patterns. While mainstream geology doesn't fully embrace these ideas, they continue to be explored. So, are earthquakes simply the product of grinding plates? Or is there more to the story? If our planet is constantly shifting, what unknown forces might still be waiting to shake up our understanding of how the Earth really works? Mechanisms of mountain formation. Mountains are Earth's greatest sculptures, but how exactly are they formed? Most people assume mountains have always been there, standing tall and unshakable. But in reality, they are dynamic, constantly growing, eroding, and even vanishing over millions of years. The real question is, what forces are powerful enough to push entire landscapes miles into the sky? The standard explanation ties mountain formation to plate tectonics. When massive sections of Earth's crust, called tectonic plates, collide, the land has nowhere to go but up, creating enormous mountain ranges like the Himalayas. The collision between the Indian and Eurasian plates, for example, continues to push Mount Everest higher by a few millimeters each year. But is this the whole story? Some scientists argue that mountains don't just form from plate collisions. Some may rise due to forces from deep within the Earth. Mantle plumes, rising columns of superheated rock, could be responsible for uplifting vast regions. Others suggest that intense erosion and climate changes may contribute, reshaping landscapes in ways we don't fully understand. Then, there's the debate over ancient mountain ranges. If plate tectonics explain modern mountains, why do we find evidence of ancient mountain belts in places where no major tectonic activity exists today? Could there be missing geological processes at play? Mountains hold the history of Earth's violent past, and yet their formation is still full of mysteries. Are there hidden forces shaping the land beneath us? Or do we already have all the answers but just need to dig a little deeper, perhaps beneath our very feet? Role of asteroids in Earth's history. What if Earth's history was shaped not by slow, gradual changes, but by sudden, cataclysmic impacts from space? Asteroids, those wandering space rocks, have a reputation for destruction, but their role in shaping our planet might be far greater than we ever imagined. Some scientists argue that without them, life as we know it wouldn't even exist. The most famous example? The Chicxulub impact, the asteroid that wiped out the dinosaurs 66 million years ago. When this 6-mile-wide rock slammed into what is now Mexico's Yucatan Peninsula, it unleashed destruction on a planetary scale. Shockwaves, wildfires, tsunamis, and a cloud of debris that plunged Earth into darkness. Without that impact, mammals, our ancestors, might never have taken over. But that's just one theory. Some researchers believe asteroids didn't just wipe species out. They may have also helped create life. Early Earth was bombarded by space debris, and some scientists think that these impacts may have delivered water, organic molecules, and even the building blocks of life itself. If that's true, then the very event that nearly wiped out life millions of years ago could be the same force that made it possible in the first place. Not everyone agrees. Some argue that Earth's geology and volcanic activity played a bigger role in extinctions and climate changes than asteroid impacts ever did. Others suggest that asteroid-delivered organic molecules weren't necessary. Life could have emerged from Earth's own chemistry. So which is it? Are asteroids cosmic harbingers of doom, or essential ingredients for life's creation? If another impact were headed our way today, would it mark the end, or the beginning of something new?